The learning outcome of terminal velocity motion laboratory. Newton's second law can be applied to a freely falling body which is acted upon by two forces. 1. Weight of the body is equal to minus mg j hat acting downwards. Secondly, the viscous drag, either B into V or B into V squared, acting upwards. When net force is not equal to 0, there is net motion in the direction of the force. These are the mathematical equations used under various conditions. For a freely falling object ignoring air resistance, only the weight is considered. For an object interacting with the surrounding, weight force plus the drag force is considered. For an object moving with a terminal velocity, the drag force is minus b into v. For an object accelerating, the drag force is minus b into v squared. The motion of a falling doll was videotaped. The observed position and the time using tracker were evaluated, which is indicated as red line in the graph. The computational model in V idle was created. Its predictions, considering only gravity, is plotted as a blue line. The gravity plus viscous drag, when they both were considered, they are plotted as green line in the graph. The, all the three graphs are plotted using Excel and are discussed. To start with, the video motion of the doll of mass 0.05 kg was dropped down from a height of 6 feet down in the y direction. The coordinate axis was chosen from the starting of the ball. Frames 1 to 18 are considered. The initial time is 0 seconds. The position to start with is 000. The last time is 0.469 seconds. The graph of position versus time looks like this. Using idle, the code used for running, considering only the gravity, is as follows. The ball's mass is input as 0.05 kilograms, initial position, initial velocity, the initial time as 0 seconds, delta t as 0.003, the g value as 9.8 meter per second squared, the j hat vector as 0, 1, 0, are a few values which are keyed in. The drag force constant B is equal to 0 was considered initially. The Python code gives the computational model's position values in a file called dollgrab.cvcsv. The loop is calculated with t less than 0.469. The net force initially is considered only due to the weight W of the ball, and in the Excel sheet, this is the tracker graph for the observed position, and this is for the computational model. Considering drag force in the Python code, this was written fnet was changed to W plus fd. Fd was defined earlier as minus b into v squared, and the arrow scale, the rate, those values are keyed in, and using the Excel spreadsheet, the position versus time graph considering drag is also plotted. When all the three are plotted in the same graph, you can see here that the observed position is plotted as a red line graph. The computational model using VIDLE is plotted as the blue line graph. When we consider the viscous drag also, it is plotted as the green line. When the motion of a doll when it is thrown down When that is considered, doll is thrown down but not dropped from the same height with an initial force. Both the times, the doll is subjected to the same acceleration due to gravity. It has higher velocity, higher initial acceleration, and kinetic energy. Position versus time graph drawn for the thrown ball coincides with that of a freely falling body, showing that both of them hit the ground at the same time. Thank you for your patient hearing.